Okay. Good evening again, everyone. This webinar will be about data acquisition with Arduino and fatigue analysis inside SOLIDWORKS Simulation. I'm Alessandro Bellini. I'm the Territory Technical Manager for Euromed and Simulation Specialist for the same territories. Euromed means Balkans, Israel, Italy, Turkey as well. And with me today there is Jose Pereiras, my colleague from Latin America. He's the Senior Technical Manager there and Simulation Specialist. Jose, hello, are you there?
Hello everyone, yes, I'm here.
Okay. So, as usual, this webinar will be recorded and you will receive a link in some days. So the objective today is about fatigue analysis, data acquisition, and to enhance and to predict the fatigue failure and to have a real-time platform for the application. We will analyze and we will see example from Resemin. Resemin is our customer in Latin America, and Jose will present the platform and all the facts that the client, the customer has developed with him. So I will talk briefly about fatigue and fatigue inside the simulation. Then we'll hear directly from Jose. So let's talk about the fatigue failure, the fatigue phenomenon. Basically, maybe as you know, fatigue is an old problem analyzed back in 1960, maybe. It's about failure after some cycles, after many cycles in a steel structure. And first of all, was analyzed back when the first flight, the first plane were having some problems on the window, basically, because of the shape, and they developed a creep after some cycles, and the cycle for a plane is about landing and taking off. But also it's related to machinery. Machinery, as in this example, the Resemin does, and it's about mining equipment. So in this case, there are two main questions. One is how to predict fatigue failure, and which are the points, which are the location of the fatigue, and of course also it's related to the time, so so to the cycle, how many cycles will develop this kind of fatigue. And so it's very important to understand the real loading excitation. So talking about Resemin, Resemin is developing mining equipment, as I said, for bolting, for making, let's say, a tunnel in security. With these steel cages, they are bolting this long bolt inside to the wall, and basically they are drilling with this machine a lot of holes. And when drilling, you know, there are a lot of vibration going on in the steel structure. So as you can see here, there is a lot of issue with the vibration and with the fracture of the main, let's say, boom. It's called a boom, and in here there is a lot of fatigue problem that I have to solve. In simulation, there is a specific module for fatigue analysis, and it's starting inside Simulation Standard. It's the very first package for simulation, and also it's related to Materiality Web Portal, because we have actually, for the customers on subscription, we have more than 100 material with the SN curve, that is called the Waller curve for material for addressing the fatigue. So fatigue analysis in Simulation Standard is very simple because it's based on the SN curve, It's very easy to use, as I will show to you in a moment, and it's based on high cycle fatigue behavior. Basically, we are addressing this problem when we have at least 100,000 cycles on the component. And we can get back damage plot and life plot. So for a simple case, fatigue, it's based on alternating stress loading. And the first one is very simple, it's fuel reverse load. It's about having the same load applied in one direction and then the other after cycle after cycle. The second one is pulsating. So basically we are calling them R equals zero, R0, because you apply the load and then remove the load, and so for that for cycle after cycles. Also, we can address the general case that is the dead load, so it's a static load plus an alternating stress. So this is called constant amplitude loading. I will show in a moment, but of course there is a more realistic situation with variable amplitude loading, and we will see in brief with Jose and the case from Resemi. So talking about fatigue analysis inside simulation, let's see very quickly what is the main, what is the elemental analysis that we can do. First of all, I have a bracket here, basically supporting some load for some components, and here you can see just a static analysis. So we have applied steel, basically an alloy. We have two forces here. You can see in purple. It's very simple. Some one force is a tensile and one is in compression. So we have also a fixture here. You can see it's fixed. So those points are fixed, those hinges. And we can check the plots, the results. For example, the stress. So it's quite intuitive to understand what is happening here. So I'm applying this load and this is the stress resulting. Also, this is a von Mises stress. Also, I can see P1 and P3. Those are the conventional maximum tensile load and maximum compression stress. The P1, of course, is a tensile, and you can see that is mostly due to this point. Also, if we go to third principal stress, the compression stress, so you can see, of course, on the contrary, it's mostly on this point, on this location. Why is this important? Because mainly for fatigue, the behavior is depending on tensile load. So we will see in fatigue that mostly due to the tensile. Why is the tensile? Because the tensile load is really developing the creep inside the component. So how to create a fatigue analysis? Very simple. This is again constant amplitude loading. So here you can see there is an event. I can edit definition, and very simply I can input that I want 500,000 cycles of this static one analysis with a fuel reverse behavior. Very simple to do that. So after that, I can get some results. The very first result is damage. So damage occurring after 500,000 cycles. And you can see in this plot, most of the structure is damaged, let's say 50% on average. But there is a point here that is basically it's failed. So after those cycles, I know basically that it's already failed due to the fatigue. But when it's failed, when the component has failed, so basically I can go to the plot of the life of the component, and I can understand here, it's very intuitive, that the minimum occurs after 71,000 cycles. So I get here the life of the component. So basically I know that there will be a creep in this position after those cycles, and then it will break due to the fatigue. So it's a very simple module, very easy to use, but again, if we're going back to the presentation, this was constant amplitude loading, but in reality, many times we have a variable amplitude loading. So let's move on and let's talk about the previous test about resemming. So this is a customer again in Latin America. They were doing some tests, for example, impact test on the equipment, on the this is called the cabin for the user. So there is a specific test for this. Also some other tests, for example, static analysis, motion, to see the loading and unloading of these bars, and so on. So they made a lot of tests. Also this one is very nice. This is about the movement of the barrels, of the head that is drilling the holes in motion. Also we can see here the simplification process that made for analyzing the fatigue and the vibration on the main, let's call it boom. This is the boom of the assembly. And so they went through a simplification here, of course. Let's see in a moment. So they removed, for example, these hydraulic cylinders. They remove, of course, all the bolts. Let's skip this part. Okay. And so this is the actual model they used for simulation. So you can see there is a remote load here that is basically it's the drilling head. Here you can see they removed the hydraulic cylinders because basically the behavior is a link, a rigid connection between those portions, and so on. So finally they get this kind of model to work on. And the first point here was about frequencies for resonance, for vibrations. So natural frequencies here. So you can see those are the first natural frequencies, because we want to analyze the vibration and also all the frequencies related. And these are the modes of vibration of that component. So as you can see, there are a lot of modes, 15, and a lot of frequency involved. Also, resemming has divided in 3 main frequency levels. So as you can see here, basically the first low frequency level is under 100 Hertz. And this was the range of operation of the machine. So basically from 48 Hertz to 56. So they concentrated their focus on this frequency level. So at this point, I would like to have the first feedback from you. I would like to know if you are using prototypes in your company. So for all the products, for only main products, or not at all. Please answer to this. Okay. Okay, just some other seconds. Okay, so we share it. So basically, as usual, mostly most of you are using only prototypes only for main products, and 33% are not using at all physical prototypes. Okay, let's move on to the second survey. So right now I'm asking you if you are already using simulation software like Flow, like simulation, like plastics, or if you are using another software for simulation, or you are not using at all simulation software. Please vote. Thank you for the feedback. Good, very good. So again, I'm showing this. So 44 of you are using already SOLIDWORKS products. 22% are not using at all simulation software, and the other are using other software as well. Okay, let's go on. So now we see with Jose the rest of the presentation about Arduino and the data acquisition. Jose, are you ready?
Yeah. Let's start with Let's start with data acquisition with Arduino.
Okay.
First of all, I would like to know who of you already know what Arduino is, or if you are working with Arduino. You have a question panel there in your GoToWebinar panel, and you can put yes or no. If you are familiar, if you know anything about Arduino, please answer yes. Otherwise, please answer no. I don't have an answer yet.
Okay, so please use the question panel to input your feedback.
Yeah. This is important because in that question panel you can ask later when we finish the presentation, you can ask your question. So okay.
Let's move on.
Okay, perfect. So what is Arduino? First of all, Arduino senses the environment by receiving input from many sensors. In this case, we use Arduino with accelerometers, only accelerometer in order to have acceleration and study those acceleration as we will see in our models. Second, Arduino is an open source electronic platform based on easy to use hardware and software. This is an advantage from other, I would say, alternative of electronic platform, because if you have an open source platform, you can think in your device that accomplish all of your requirements, as we did. Finally, you can tell your Arduino what to do by writing code in Arduino programming language and using the Arduino development environment. I have to say, I am not a specialized programmer, and I started using Arduino as it was a kind of Visual Basic, a basic C, C#, whatever. So all of those three parameters, I think, make Arduino successful for this kind of implementations. Okay, about the data acquisition, what is our motivation? Some simulation models need more detailed loading input data. When I say that, I mean that you already saw the model from Alessandro. Alessandro already knew the loading, but in the case of in many cases in real world, we don't have those pattern of loading. So it is needed to to know the load pattern is already an unknown for the analyst. And about the objectives, we have three objectives. First, more accurate simulation models. Second, avoidance of fatigue failure. And third, real-time tool for controlling fatigue failure. This, and the last one, the real-time tool for controlling fatigue failure, actually was our biggest challenge with the customer. And I will show you in a moment how we did that. Okay, let's start with our first steps using Arduino. As I said, this is our first implementation, very basic implementation. You are seeing there a bin of boot with the Arduino Mega 2560. And when I hit with my hand, you can see the vibration in the bin. And that vibration is already recorded in a very, we can see, in a very accurate way, because we are having not only the shape of the frequency, the period of the frequency, we are already having the damping, right? What we have from Arduino? We have that signal, we post-process that signals, and we get the frequency, and in this case is 39 Hertz. 39 Hertz, if you saw the result from Alessandro, when he showed the frequency from the machine, the first frequency was 38 Hertz. So that very simple example shows that we can use Arduino for getting real world cases frequency. So let's move on with the shape of that bin. What we did with Arduino, actually, we got only, I would say, this is totally, they fit our requirement. We got the three first natural frequencies. Those are 40 Hertz, 143, and 431 Hertz. But with SOLIDWORKS Simulation, we can not only verify those three frequencies, we can also have the frequency mode shapes. In the case of mode 1, F1, F2, and F3. So what I want to mean with this kind of plot, that you can combine all the technology from Arduino instead of verifying what are the real world frequency, and including SOLIDWORKS Simulation in order to have a deeper approach in your analysis. So this is a very simple example. What about the real world example? So what we see here is the machine. This is, as Alessandro said, this is a bolter. A bolter, it goes into the mine in order to drill some bars and put the mesh, a steel mesh over there. And the red boxes, if you see here we have the red boxes with the Arduino implementation. The red box is only to protect the Arduino, and also in order to install into the machine. So let's see now a lab test, a real world lab test. As you can see here, we are drilling a block of concrete, and right now we are acquiring acceleration. I will show you in a moment. In those red boxes, we have two accelerometers, accelerometer 1, accelerometer 2, and we are sending the signal through Bluetooth receiver. This was actually our first implementation. Right now, we improved that implementation, and we are recording all the acceleration in the memory card. As soon as we started drilling with a frequency of 48 Hertz, we can see the movement of the machine. Actually, that vibration is causing the fatigue failure. So imagine more than 2,000 kilos drilling at 48 Hertz is a very hard loading on the machine. So high stress cycles, fatigue, and component failure are reported, yes, in the mine. In this case, of course, we didn't have any failure because it was a lab test, but after doing this, we recorded the data from Arduino, and we got these 3 plots. As you can see, I guess nobody can guess what the frequency is. So what we did here is just take a moment in the signal where the drilling was started, and after post-processing this signal, we get that number, you know. This is, I would say, this is the main number that Alessandro already showed, the 38 Hertz. That number, 38 Hertz, verified that we did with SOLIDWORKS simulation is the same. We are getting the same result. So at this point, we are very confident with our result. I have to tell you the truth. When we started analyzing our model in SOLIDWORKS simulation, we didn't get 38 Hertz. We get another number, another frequency. So using Arduino helped us to adjust our simulation model, and finally we get very good shape results. So let's move on now. How we bridge the SOLIDWORKS simulation and data acquisition. We focus on 2 types of models. The first model on your left is the predictive model. That model is based on acquiring with Arduino acceleration. That has a model of fatigue simulation using those accelerations as an input. That model is actually the SOLIDWORKS simulation model. And finally, as Alessandro already showed, we can predict the live prediction failure in the structure. So I would say this is the most common. All of those who already said that they are using simulation, I guess this is the most common model for simulation. But on your right, you have the real-time model. The real-time model is actually, it was our, as I said, it was our biggest challenge with the customer, because this real-time model had to predict in real time, online, what is going on with the structure. So the model is very similar to the previous one. We get the acceleration from Arduino, but instead of calculating all the time the simulation result, we already have all of those data. So we are using a kind of interpolation tool. We have many. In order to say one, we can say artificial neural network. So we put all of those information from SOLIDWORKS simulation and feeding our model with those acceleration from Arduino, we can have a real-time prediction tool on the machine. Actually, the customer is selling that tool for their customer just a marginal price comparing with the machine, right? So in order to say the implementation, right now I'm showing you, you already know this. Actually, what I'm going to do now is getting the natural frequency from the model. This is already known. This is the natural way to do in SOLIDWORKS simulation. You can get the frequencies and the period of your model. So nothing new, still nothing new. There, on your left, on the top, you see what we already developed. This is an API. API is Application Programming Interface. In this case, the very beginning use of this API is in order to get in an easy way, the two natural frequencies from simulation. So, now, up to now, what we did is very simple. Just a button and getting the two natural frequencies. Let's move on now with Arduino. Actually, now we are connecting with Arduino. Arduino in our model is printing a file, and we are getting those frequencies from Arduino, the two natural frequencies. Actually, Arduino, it is not only calculating, getting the result, it's also calculating the natural frequency. Yes? Many times my user, my customer asks, Jose, how can I get the damping? In this case, we are getting the damping with data acquisition. This is another use you can do with Arduino. So it is very important when you are running a dynamic simulation, because in dynamic, in order to have, I would say, accurate result, you have to have the damping factor. So this is one way, a very good way to have the damping factor. Of course, you have books, you have internet sometimes that can help you. But from my point of view, this is the most accurate way to get the damping factor.
Yeah, and also we have to say that it's very cheap to have this kind of data because of the Arduino open source, and those kinds of sensors are not so expensive.
Yeah. This is a very good highlight, because when we started with regular electronic platform, I remember the prices. It costed almost $10,000, and this implementation we spent I would say $500 to complete this implementation. So as you said, Alessandro, Arduino makes the difference also from the price point of view. Now what you are seeing here is I would say now this is the bridge, the real bridge between Arduino and SOLIDWORKS simulation. We are identifying from SOLIDWORKS simulation what are the real natural frequencies that are exceeded by the loading, you know. So this could be a nightmare for an analyst if they don't know anything about the machine, as when we started with analyzing this device. And finally, we develop what we call the analyzer, the fatigue analyzer. As you can see, the analyzer is said, the intention is saying in real time that is remaining only 1,500,000 cycles to get a failure. And for those who are using Arduino, you may know that in Arduino you are connecting to the serial port. In this case, we are connecting to the serial port directly from SOLIDWORKS simulation. So that allows us to process in real time those these are the acceleration, process this acceleration, and having the real time tool in our SOLIDWORKS simulation. Also, I have to say, it is not needed to run simulation in order to get the result. With this kind of API, you can have running this API connecting to your simulation results, and you are getting a standalone tool on your machine, of course. Okay, let's see some details for those who are interested on the details of the implementation. This, the final implementation was done with Arduino Pro Mini. When I say Arduino Pro Mini, the size of this, it keeps in a half of the hand. So it is very, very small, and you can put the, I would say, in almost every machine. And about the accelerometer, we started with a digital accelerometer, but finally we get the MPU 6050 accelerometer. This is a digital accelerometer, and this allows us to get acceleration in 4 kilohertz. That means 4 kilo. Imagine that if the machine is 38 hertz, getting result at 4 kilohertz is much more than needed. So I can say is very accurate for every kind of application that we can imagine in machinery. Finally, following the same workflow that Alessandro did with that bracket, we started with a static simulation in SOLIDWORKS. We identify what were the most stressed areas, and finally get result from the static point of view. With those von Mises stresses, we calculated actually our fatigue failure, and that makes us happy, very happy, because we got the same result that we saw on the field. On your left, you have the fail machine with the fatigue factor, and in SOLIDWORKS simulation, we are getting, of course, with the help of Arduino, we are getting the same area in our virtual model, right? Regarding the product, or Alessandro already talked about the product, and finally, I would like to finish with Alessandro talking about conclusions and finally questions.
Okay, thank you, Jose, very much. I'm switching into my screen. Okay, so to finish up this webinar, basically, as always, I'm pointing out the value of virtual simulation, as we saw today for SEMIN, but for other cases as well. And the most interesting thing is that about these numbers, these figures, that tells us that using virtual simulation as soon as possible in the workflow, it's giving you a lot of benefits. As we see quality targets or revenue targets or launch dates and so on. So it's very interesting to have a virtual simulation tool and use it as soon as possible in the workflow. So talking about the final section, I would like to ask you for the interest that this webinar has raised. So please answer. So it's very important, your feedback here. Okay, some seconds to vote. Okay, very good. As always, I would like to share with you. So thank you very much for the feedback. And the last question is about having being contacted about SOLIDWORKS simulation if you need some more information about fatigue, but of course all other modules and other product about simulation. So let me have your feedback. Some other seconds. Okay. Very, very good. So again, also I will share this 83%. I'm very happy. So thank you again for this. So as the last part, I would like to answer your question. If you have, those are my references. If you want to write to have some other information, or to Jose, of course. Also, if you want to search for my YouTube channel. At the moment, I don't see any question about fatigue. So if you have, please use the panel on the GoToWebinar, or otherwise we will finish. Jose, do you want to add something about the resamin case for fatigue?
No, only to say thank you very much for the assistance. If you like to later to send an email to us with any question, we will open to answer.
Okay, thank you, Jose, very much. Thank you all for your attention, and see you next webinar. Bye-bye.
Bye-bye.